Look at your watch. Listen to it tick. Each second follows the next in perfect, unwavering rhythm. Time, we think, is absolute, universal, the same for everyone everywhere. A second on Earth is a second on Mars, a second in the depths of intergalactic space. This seems obvious, self-evident. It's what our senses tell us, what our everyday experience confirms moment by moment, day by day, year by year. But something strange happens when you follow Einstein's math. In the early years of the 20th century, a young patent clerk in Bern, Switzerland, sat at his desk and asked a simple question: what would the world look like if I could ride on a beam of light? It was a thought experiment, a game of the imagination. But when Albert Einstein followed the mathematics to its logical conclusion, when he took the equations seriously and pursued them wherever they led, he discovered something extraordinary. He discovered that the universe doesn't work the way our senses tell us it does. He discovered that time is not absolute, that space can bend, that mass and energy are the same thing wearing different masks, that the speed of light is not just fast, it's the cosmic speed limit woven into the very fabric of reality itself. These weren't philosophical musings. They weren't poetic metaphors. They were mathematical necessities. When you write down the equations that govern light and motion, when you insist that the laws of physics must be the same for everyone, regardless of how fast they're moving, the math itself demands these strange conclusions. Einstein didn't impose his will on nature. He listened to what nature was telling him through the language of mathematics. And what nature told him was astonishing. Imagine two twins, identical in every way. One stays on Earth. The other boards a spacecraft capable of traveling at 90% of the speed of light and journeys to a nearby star system and back. When the traveling twin returns, she steps off the spacecraft younger than her sibling who stayed behind. Not metaphorically younger, not psychologically younger, actually, physically, measurably younger. Her cells have divided fewer times. Her heart has beaten fewer beats. Less time has literally passed for her. This is not science fiction. This is what Einstein's equations require. It's called time dilation, and it's been measured, tested, and confirmed thousands of times. We've put atomic clocks on airplanes and flown them around the world. When they land, they tick slightly fewer times than identical clocks that remained on the ground. The difference is tiny, mere billionths of a second, because the airplanes weren't going anywhere near the speed of light. But the effect is real. It's measurable. It's there. The global positioning system satellites orbiting above our heads experience time dilation every moment. They're moving at about 14,000 kilometers per hour relative to us on the surface. At that speed, time passes slightly faster for them than for us. Without corrections for Einstein's relativity built into their programming, GPS would accumulate errors of several kilometers per day. Your phone knows where you are because engineers took Einstein's strange mathematics seriously. But why does time slow down when you move fast? The answer lies in understanding what light is and what it does. Light is strange. It's a wave, but also a particle. It travels through empty space without needing any medium to carry it. And most peculiar of all, light always travels at the same speed, no matter who's watching it or how fast they're moving. Think about that for a moment. If you're standing still and I shine a flashlight, you measure the light traveling at about 300,000 kilometers per second. Now imagine you hop on a spacecraft and fly toward the light at half the speed of light. Your intuition says you should measure the light approaching you faster at speed plus your speed, but you don't. You measure exactly the same speed, 300,000 kilometers per second. Now fly away from the light source at half the speed of light. Your intuition says the light should be catching up to you more slowly. But again, you measure exactly 300,000 kilometers per second. Light doesn't care how fast you're moving. It always travels at the same speed relative to you. This strange, stubborn, experimental fact about light is what forces time to be flexible. Einstein realized that if the speed of light must be constant for everyone, then something else has to give. And what gives is time itself and space. They stretch and compress, bend and flex to ensure that light always travels at the same speed no matter who's measuring it. When you move fast, your time slows down relative to someone who's moving slowly, not because there's something wrong with your clock, but because time itself, the fundamental flow of causation, the progression from past to future, runs at different rates depending on your motion. And it gets stranger still. Einstein's most famous equation, E equals mc squared, emerged from these same considerations about light and motion. It's been printed on t-shirts, referenced in movies, scrawled on countless blackboards. But do we truly understand what it means? Energy equals mass times the speed of light squared. It tells us that mass and energy are not separate things. They're the same thing in different forms. Mass is frozen energy. Energy is liberated mass. The speed of light squared, that enormous number, 9 times 10 to the 16th meters squared per second squared, is the conversion factor between them. A single kilogram of matter, if you could convert it entirely to energy, would release 90 quadrillion joules. That's roughly the energy of 20 million tons of TNT. The atomic bombs that ended World War II converted less than a gram of matter into energy, and look what they did. A gram, less than the mass of a paperclip. This isn't theoretical. Every star in the sky is a furnace where mass transforms into energy. In the core of our sun, every second, 4 million tons of matter cease to exist as matter and become pure energy. That energy radiates outward, and 8 minutes later, a tiny fraction of it falls on your face as sunlight. You are being warmed by Einstein's equation. You are alive because E equals mc squared. And it means something even more profound. The atoms that make up your body, the carbon, nitrogen, oxygen, iron, were forged in the hearts of stars that lived and died before our sun was born. Those ancient stars converted hydrogen into heavier elements through nuclear fusion, a process that works only because mass and energy are interchangeable. When those stars exhausted their fuel and exploded as supernovae, they scattered those elements into space. Eventually, some of that cosmic debris coalesced into a new star, our sun, and its attendant planets, including Earth. We are made of star stuff, not poetically, not metaphorically, literally. The atoms of your body were manufactured in stars. You are a way for the cosmos to know itself. And none of it would be possible if Einstein's strange mathematics weren't true. But there's more. Einstein didn't stop with special relativity, the relativity of time and space for objects in uniform motion. He pushed further. He asked, what about gravity? What about acceleration? For 10 years, he struggled with this question. 10 years of false starts and dead ends and equations that almost worked but didn't quite. And then in 1915, he had it. General relativity. The geometric theory of gravitation. Newton had told us that gravity was a force. Massive objects attract each other across empty space through some mysterious gravitational pull. It worked beautifully. It predicted the orbits of planets with exquisite precision. But it left unanswered the question, how does gravity work? How does the Earth know that the sun is there 93 million miles away? How does the sun reach across that void and pull on the Earth? Einstein's answer was radical. Gravity isn't a force. Gravity is geometry. Imagine space as a fabric, A flexible sheet stretched taut. Place a heavy ball on the sheet and it creates a depression, a curvature. Now roll a smaller ball across the sheet. As it approaches the depression, it curves inward, attracted not by any force emanating from the heavy ball, but simply by following the curved geometry of the sheet. This is what mass does to space, and not just space-time, the unified four-dimensional fabric of reality where space and time are woven together. Massive objects curve space-time around them. Other objects, including light itself, travel through this curved space-time. They follow the straightest possible paths called geodesics. But in curved space-time, even the straightest path is curved. The Earth orbits the sun not because it's being pulled by a force, but because the sun curves space-time around it, and the Earth is simply following the natural contours of that curvature. We call it orbiting, but from the Earth's perspective, it's moving in a perfectly straight line through curved space-time. When Einstein published these equations, they made a prediction. If the sun curves space-time, then light from distant stars should bend as it passes near the sun. During a solar eclipse in 1919, astronomers measured the positions of stars visible near the sun's edge. The stars appeared slightly displaced from their normal positions, exactly as Einstein's equations predicted. Space-time was curved. The geometry of the universe was non-Euclidean. The headlines around the world proclaimed, "Lights all askew in the heavens." We've since found much more dramatic evidence. Entire galaxies act as gravitational lenses. Their immense mass bending light from even more distant galaxies behind them, creating multiple distorted images of the same object. We've detected gravitational waves ripples in space-time itself created when black holes collide and merge, events so violent they shake the very fabric of reality. In 2019, we photographed the shadow of a supermassive black hole, an object so dense that it curves space-time into a one-way trap from which not even light can escape. All of this from following the mathematics. Einstein's equations also make another strange prediction. If you stand on the surface of the Earth and I float in space far from any gravitational field, my time runs faster than yours. Gravity slows time. The stronger the gravity, the slower time passes. This effect is called gravitational time dilation. It's subtle for everyday gravity. If you spend your life in the basement and I spend mine in the attic, when we meet in old age, I will be very slightly older than you, a few microseconds perhaps. But near extremely massive compact objects like neutron stars or black holes, the effect becomes dramatic. Imagine falling toward the event horizon of a black hole. From your perspective, you fall inward in a finite time. But from my perspective, watching from a safe distance, you never quite reach the horizon. Your time slows more and more as you approach. Your signals to me become more and more redshifted. You appear to freeze at the edge, hovering eternally at the boundary of no return. Which perspective is right? Both. Each of us experiences time validly from our own reference frame. There is no absolute universal time keeping score. Time is local, personal, relative. This brings us to perhaps the strangest implication of Einstein's mathematics, the cosmic speed limit. Nothing can travel faster than light. Not because we haven't built a fast enough engine, not because of some technical limitation we might overcome someday, but because the mathematics of space-time forbids it. Look at what happens in Einstein's equations as you try to accelerate an object closer and closer to the speed of light. The object's mass effectively increases. At 90% of light speed, it has more than twice its rest mass. At 99%, more than 7 times. at 99.99%, more than 70 times. As you approach the speed of light, the object's mass approaches infinity. And to accelerate an infinite mass requires infinite energy, which is impossible. The speed of light isn't just a speed limit. It's a fundamental feature of causality itself. If you could travel faster than light, you could, under the right circumstances, arrive before you left. You could be in two places at the same time. Cause and effect would break down. The universe would become paradoxical, contradictory, nonsensical. Light itself travels at this cosmic speed limit precisely because photons have no rest mass. For anything with mass, the speed of light is forever unreachable. This seems limiting. It means we can never traverse the vast distances between stars quickly. It means the universe will always be a largely unexplored mystery to us. But it also means the universe has order, structure, logic. The past is separate from the future. Causes precede effects. Reality makes sense. Some have suggested we might circumvent this limitation through wormhole shortcuts through space-time connecting distant regions. Einstein's equations permit such solutions mathematically. But creating and stabilizing a wormhole would require exotic matter with negative energy density, something we've never observed and may not exist. The universe's speed limit may have loopholes, but if so, they're hidden deep within mathematics we don't yet understand and physics we haven't yet discovered. What Einstein did was show us that the universe operates according to principles very different from our everyday intuitions. Time is not absolute. Space is not fixed. Mass and energy are equivalent. Gravity is not a force but curved geometry. The speed of light is built into the architecture of reality. These aren't abstract philosophical claims. They're practical realities, GPS satellites, particle accelerators, nuclear power, the light from distant galaxies, the very atoms of our bodies. All of these exist and behave as they do because Einstein's strange mathematics describes reality correctly. But why should mathematics describe reality at all? Why should symbols on a page, abstract logical structures invented by human minds, have anything to do with how the universe actually works? This is one of the deepest mysteries in science. The physicist Eugene Wigner called it the unreasonable effectiveness of mathematics in the natural sciences. We invent mathematical structures to describe patterns we observe, but then those same mathematical structures predict phenomena we've never observed. We follow the mathematics into strange territory, and nature is there waiting for us. Einstein predicted gravitational waves in 1916 using pure mathematics. We detected them for the first time in 2015, a century later. The mathematics knew they were there all along. Maxwell's equation predicted electromagnetic waves traveling at the speed of light before anyone knew what light was. Dirac's equation predicted antimatter before positrons were discovered. The equations of quantum mechanics predicted quantum entanglement, which Einstein himself found so disturbing he called it spooky action at a distance. Yet experiments confirm it happens. Mathematics is our best tool for seeing beyond the limitations of our senses. We evolved to navigate a world of medium-sized objects moving at moderate speeds under gentle gravity. Our intuitions are calibrated to that environment, but the universe is far stranger than our evolutionary heritage prepared us to understand. At high speeds, approaching light speed, time dilates and length contracts. At very small scales, the quantum realm, particles exist in superposition and measurement affects reality. At enormous scales, cosmic distances, space itself expands. At extreme densities, black holes, space-time curves so severely it traps even light. None of these regimes were accessible to our ancestors on the African savanna. Evolution gave us no instinct for relativistic speeds or quantum uncertainty or curved space-time. But evolution did give us something remarkable, the ability to do mathematics. And mathematics extends our vision beyond our biology. When Einstein followed the mathematics, he discovered that simultaneity, the concept of two events happening at the same time, is relative. Whether two distant events occur simultaneously depends on your motion. There is no absolute now extending across the universe. Different observers moving differently slice up space-time into past, present, and future in different ways. Your now and my now are different. This seems impossible. It violates our deepest intuitions about time. But it's what the mathematics requires, and it's what experiments confirm. The Hafeld-Keating experiment in 1971 put atomic clocks on commercial airliners and flew them around the world in opposite directions. When they landed, the clocks showed different times, exactly as Einstein's equations predicted. The eastbound clock lost time. The westbound clock gained time. The clocks disagreed on how much time had passed. Which clock was right? All of them. Each measured time correctly from its own reference frame. This relativistic view of time has profound implications for how we think about existence. Is the future already out there, just as real as the past, with our experience of now, merely spotlighting different moments as we move through time? Or is the future genuinely undetermined, coming into existence moment by moment as time flows forward? Einstein's mathematics doesn't answer these philosophical questions definitively, but it constrains our options. It tells us that time is not what we thought it was. It's not a universal river carrying all of us along at the same rate. It's something more subtle, more personal, more woven into the structure of space and matter and motion. Some physicists take this to mean that all moments in time exist equally past, present, and future together in an eternal block universe. From this perspective, the flow of time is an illusion created by our consciousness, which experiences moments sequentially even though they all exist simultaneously in the larger space-time structure. Others argue that the future is genuinely open, that quantum mechanics introduces true randomness and unpredictability, and that reality unfolds moment by moment in ways that cannot be determined in advance. The mathematics allows both interpretations. Perhaps one day we'll have a deeper theory that resolves this question, or perhaps the nature of time will remain one of those profound mysteries that mathematics can describe but not fully explain. What we can say with certainty is that time is strange, stranger than our intuitions suggest. And we know this because we followed Einstein's math. There's a kind of courage required to do what Einstein did. It's the courage to take your equations seriously, even when they tell you things that seem impossible. To trust the mathematics, even when it contradicts your intuition. To follow the logic wherever it leads, even into territory so strange it seems like it must be wrong. Einstein could have stopped. He could have said, this can't be right. Time can't slow down. Space can't curve. Mass can't be energy. He could have dismissed his own conclusions as mathematical curiosities with no physical meaning. Many did exactly that when his papers were first published. But Einstein trusted the mathematics, and he trusted nature. He believed that the universe operates according to logical principles we can discover and understand, even if those principles seem bizarre from our limited human perspective. He was right to trust. Every test we've devised, every experiment we've performed, every observation we've made has confirmed his strange predictions. Time dilation is real. Length contraction is real. Mass energy equivalence is real. Curved space-time is real. The cosmic speed limit is real. The cosmic speed limit is real. We live in Einstein's universe, a universe far stranger and more wonderful than the one our senses perceive directly. A universe where time is elastic, space is curved, and the cosmic speed limit is written into the fundamental laws of nature. This doesn't make the universe less comprehensible. It makes it more comprehensible. Before Einstein, we had mysteries without explanations. We had gravity, but we didn't know what it was. We had light, but we didn't fully understand it. We had time and space, but we treated them as separate, absolute entities. Einstein showed us that these mysteries were connected, that gravity, light, time, space, matter, and energy are all part of one unified description of reality. His equations didn't make the universe more mysterious. They revealed deep connections and patterns we hadn't recognized before. And they did something else. They showed us that the universe is knowable, that by using our minds, by thinking carefully and following mathematics honestly, we can understand how reality works at the deepest levels. We can see beyond the limitations of our senses. We can discover truths about the universe that are not obvious, not intuitive, sometimes not even believable, but nonetheless real. This is the power of science. Not that it tells us comfortable truths or confirms our intuitions, but that it reveals uncomfortable truths that expand our understanding. Science is a way of asking nature what's really going on, and then listening carefully to the answer, even when it's not what we expected or wanted to hear. Einstein listened, and what he heard transformed our understanding of reality. Today, more than a century after Einstein published his theories, we continue to find new confirmations of his mathematics. The detection of gravitational waves opened a new window on the universe. The imaging of black hole shadows gave us visual evidence of space-time curvature. Precision atomic clocks test relativity to ever greater accuracy. GPS systems depend on relativistic corrections. Particle accelerators probe mass energy equivalents at extreme energies. All of it works. All of it confirms what the mathematics predicted. And yet, Einstein's work is not the final word. We know his equations are incomplete. They break down at the centers of black holes where densities become infinite. They don't incorporate quantum mechanics, the equally strange but different theory that governs the atomic realm. We don't yet have a unified theory that combines general relativity and quantum mechanics into one coherent description. Somewhere beyond Einstein's mathematics lies an even deeper truth waiting to be discovered. Some future physicists will find equations that encompass both relativity and quantum mechanics, that describe what happens at the Big Bang and inside black holes, that reveal the next layer of reality's structure. When that happens, it will likely seem as strange and counterintuitive as Einstein's relativity seemed a century ago. The mathematics will again tell us things that seem impossible. And if we're wise, we'll listen, because that's what mathematics does. It extends our vision beyond biology, beyond intuition, beyond common sense. It lets us see the universe as it is, not as we expect it to be. Einstein followed the math, and he found a universe where time flows at different rates for different observers, where mass and energy are two forms of the same thing, where gravity is the curvature of space-time, where there's a cosmic speed limit built into the fabric of reality, where simultaneity is relative, and the future is already written in the geometry of space-time, or perhaps still being created moment by moment. We're not entirely sure which. These strange conclusions weren't imposed on nature. They were revealed by nature through the language of mathematics. Einstein was humble enough to listen. We are privileged to live in an era when we understand these truths, when we can look up at the stars and know that we're seeing light that has traveled for millions or billions of years across curved space-time, when we can hold a smartphone and know that it works because someone took Einstein's strange mathematics seriously, when we can say with confidence that we understand something deep and true about how the universe works. Not everything, not even close to everything. The universe still holds countless mysteries, but something real and profound and wonderful. This is the gift Einstein gave us. Not just equations, though the equations are beautiful. Not just practical applications, though those have changed our world, but a deeper understanding of reality, a vision of a universe more intricate and elegant than we imagined, and the knowledge that by following mathematics wherever it leads, we can glimpse truths that transcend our everyday experience. Something strange happens when you follow Einstein's math. You discover that the universe is stranger than you thought, and more beautiful and more knowable. You discover that reality exceeds imagination, that truth is more wonderful than fiction. You discover that time, space, matter, and energy are woven together in ways our senses cannot directly perceive, but our minds can understand. And in that understanding, there is wonder, there is beauty, there is a kind of cosmic poetry written in the language of mathematics. We are, each of us, part of that cosmos, made of atoms forged in stars, riding on a planet curved space-time through the curvature of space-time, living in a universe where following the mathematics reveals wonders our ancestors never dreamed of. Einstein showed us the way. He followed the math, and the math revealed the universe.